Observing the universe beyond our solar system, we hit a hard physical limit. Space is so immense, our perspective shrinks to a single glowing pixel. With the exception of our own sun, no ordinary telescope can resolve the physical disk of a star. A star could be 100 times the size of Jupiter, but the distance renders it identical to a tiny dwarf. They both register on our detectors as featureless, unresolvable points of light. Facing this limitation, astronomers can measure exactly 3 distinct properties from that point of light. First, we can measure its precise position on the celestial sphere. Second, we can measure its apparent brightness, which is the actual flux of light energy hitting our telescope mirrors here on Earth. And third, we can measure its color, breaking that light apart to see the specific spectrum of wavelengths it emits. The central challenge of modern astrophysics is building a complete 3D physical profile of a distant world using only these 3 sparse, 2-dimensional data points. To solve this, we rely on the astrophysicist's inverse problem. We have the final signal, the light hitting Earth, and we have to reverse engineer the source that created it. The math works because of one critical assumption. The laws of physics that operate locally in our laboratories apply identically across the entire cosmos. We employ a specific sequence of tools. Geometry, thermodynamics, and quantum mechanics each serve as the prerequisite for the next stage of the derivation. This derivation is a chain reaction. Distance unlocks the calculation for power, and power reveals the true size. We do not guess the nature of stars. We use physical laws to mathematically force them to reveal their exact mass, energy, and scale. Step 1 begins with geometry, using trigonometric parallax to determine a star's distance. Earth's orbit provides a baseline of 2 astronomical units. Observing a star 6 months apart reveals a parallax angle shift against background stars. Using trigonometry, distance equals this baseline divided by the angle. 1 arcsecond equals 1 parsec away. With the distance established, we move to step 2, calculating the star's absolute power output, or luminosity. Starlight captured on Earth is flux. As light travels outward, it spreads over a larger area, following the inverse square law. But surface brightness remains constant, because the flux drop is perfectly offset by a proportional drop in the star's solid angle. To find the total energy emitted, we multiply our measured flux by the surface area of the massive sphere defined by our parallax distance. By measuring how dim a star looks and tracking Earth's motion to find its distance, we have calculated its absolute power output. Next, in step 3, we extract the star's surface temperature by analyzing its observed color. The violent collisions of atoms in the stellar surface approximate a state of thermodynamic equilibrium. This causes the star to emit thermal radiation in a continuous pattern known as a black body spectrum. This chart shows the spectral energy distribution. As the star gets hotter, total flux increases and the curve shifts. Following Wien's displacement law, the emitted light's peak wavelength is inversely proportional to the surface temperature. By finding the exact color where light peaks and applying Wien's law, the surface temperature is identified. Now we have the variables required for step 4, deducing the physical radius of a star without ever seeing its edge. The Stefan-Boltzmann law dictates luminosity is determined by surface area and temperature to the 4th power. With luminosity and temperature already derived, we rearrange the algebra to isolate the radius squared, revealing the star's absolute physical size. The strict laws of thermodynamics force the isolated star to reveal its exact physical volume through pure mathematical deduction. For the final step, we deduce the exact chemical composition by looking at small imperfections hidden inside its light. This high-resolution solar spectrum is not a perfectly smooth curve of colors. It is interrupted by thousands of dark vertical bands known as Fraunhofer lines, representing specific wavelengths of light that went missing before reaching Earth. The light is missing because cooler gas in the star's outer atmosphere acts as a filter, absorbing specific photons emitted by the hotter interior. Driven by quantum mechanics, atoms only absorb a photon if its energy matches the quantized jump between their electron levels. Every element has unique electron shells, so when they absorb light, they leave a distinct quantum barcode. By matching these barcodes to laboratory data, we read the exact mass fractions of hydrogen, helium, and metals in the star's atmosphere. This stacked chart displays the OBAF-GKM spectral classification system. As surface heat increases, atoms get stripped of electrons in a process called ionization. This changes the barcode, providing a secondary, precise confirmation of the star's temperature. The smallest quantum structures in the universe allow us to physically dissect the chemical makeup of its largest objects. This is the complete chain reaction of the astrophysicist's inverse problem. Measuring position yielded the parallax angle. That angle gave us the distance. That distance enabled calculation of luminosity. Measuring peak color yielded surface temperature. Combining this with luminosity revealed radius. Analyzing missing light yielded quantum barcodes, providing the exact chemical composition. The abstract data resolves into a physical reality. These final dimensions are not estimates. They are rigorous deductions constrained by local, immutable rules, like the Stefan-Boltzmann law and Maxwell's electrodynamics. By trusting the physics observed on our planet, we project human understanding across thousands of parsecs, rendering mere points of light as fully realized, measurable worlds.